Hello, good morning. Today we will see properties of Fourier transform and discrete Fourier transform. Because most of the properties go in line, I am not discussing separately properties of Fourier transform and properties of discrete Fourier transform, but we combine it. The first property is linearity, then we have time shifting, time scaling, time differentiation, time integration, conjugate property, frequency shifting, convolution, modulation, duality, time bandwidth product, and Parseval's relation. So firstly start with linearity. So as I have already mentioned, we always deal with linear time invariant systems, that is LTI systems. So linearity is bound to hold good. That means if you have two different signals x1 and x2 and if they are linearly combined, the transform will also be linearly combined with the same scale. Physical significance of linearity. So what we can do is we can divide the signal into number of combination of two or more component signals. We can scale it and add it up, and then we can find Fourier transform of each component separately and then linearly add it to generate the Fourier transform of the combination. Similarly, if the signal can be decomposed into linear combination of two or more component signals in Fourier domain, then inverse Fourier transform can also be calculated for individual components, and this is what we do when we are using partial fraction expansion. Second property is time shifting property. So whenever the input is just translated by time t0, so instead of xt we have x of t minus t0. What happens in the Fourier domain is the corresponding Fourier transform will be multiplied by e raised to minus j omega t0. That means the magnitude response will remain the same, only there will be change in the phase. So physical significance of time shifting property. Fourier transform coefficients for the time shifted signal will have same magnitude, but the phase angle is negative of the phase angle of the Fourier transforms of original signal, and there will be some phase shift as we have seen e raised to minus j omega t0. Fourier transform coefficients of the time reverse signal will be a complex conjugate of Fourier transform coefficients of the original signal. This is when instead of xt we are considering x of minus t. What is the use of this? If you have two templates and if you want to compare whether they are same only just means they are same only thing is they are time shifted, then we can compare the magnitude response, and if the magnitude response is the same we can say that the two templates are the same, they are matching, only thing is there is some time shift. Then time scaling property. So if you scale the signal xt by a factor of a, if you have x of a t, then the transform will be 1 upon magnitude of a x of j omega divided by a. That means the Fourier transform will also be scaled by the same factor, and there will be the amplitude of the means Fourier coefficients will have the scaling factor of 1 upon mod a. Physical significance of time scaling. Fourier transform of the time scale signal with scaling factor a will have both magnitude and phase inverse scale, phase inverse scaled by a factor of a. Consider for example perceiving the higher pitch of the recorded sound. So when we play it at the same higher speed, so when the recorded sound is played again with higher speed, the time domain signal gets compressed. That means it is scaled, and this expands the frequency domain signal which is perceived as higher pitch. So this is the beauty. Time differentiation property. So instead of x of t, if you have d dt of x of t, then the transform will be multiplied by j omega. That means the corresponding frequency for every particular frequency component, it will multiply by the corresponding frequency value. So what is the physical significance of time differentiation? When the signal is differentiated in time domain, its Fourier transform is multiplied by j omega. Hence, after time differentiation, the higher frequencies, suppose you consider higher values of omega, they are enhanced in the frequency domain, and lower frequency components will be reduced on the other hand. So in this case, what will happen to DC component? When omega is equal to 0, DC component will be eliminated. So that is the important point you have to consider. DC component will be destroyed when the signal is differentiated. For the differentiated signal, Fourier transform of the differentiated signal will be 0 at omega equal to 0. Time integration property. So now instead of x of t, if you have integration minus infinity to t x of tau deta, that is the signal is integrated up to time t, then what happens to the Fourier transform? The Fourier transform gets divided by j omega. So what is the physical significance? When the signal is integrated in time domain, its Fourier transform gets multiplied in time by 1 upon j omega. So the Fourier transform is multiplied by 1 upon j omega. The integration equation exists and applies only to signals with 0 DC value. So if integration equation exists and applies only to signals with 0 DC value. So DC component is not there, that we are assuming, that means omega is not equal to 0. Otherwise 1 upon j omega will tend to infinity. Integration is basically a smoothing operation and it smoothes the signal. The smoothing in time de-emphasizes the high frequencies as it is indicated by the factor omega in the denominator. So in case of differentiation, the high frequencies are enhanced and low frequencies are reduced. But in case of integration, the high frequencies are reduced, they are de-emphasized. This is the significance of integration property. Conjugate property. If xt transform to x of j omega, x star t, which is the complex conjugate of xt, considering that x of t is a complex thing, then the Fourier transform will be complex conjugate of x of minus j omega. Physical significance of conjugate property. Fourier transform of the conjugate of the signal appears on the negative frequency side and is conjugate of the Fourier transform of the original signal. If the signal is real, Fourier transform coefficients for the signal show the complex symmetry, its conjugate symmetry. So it does not change. Frequency shifting property. If x of t transform to x of j omega, then e raised to j omega 0 t, that means we are shifting in frequency domain omega minus omega 0. What happens in time domain is it is multiplied by e raised to j omega 0 t. That means the corresponding phase angle changes for x of t when the frequency shift occurs in the Fourier domain. So when Fourier transform of the signal is shifted in the frequency domain by omega 0, the inverse transformation leads to a phase shifting of the signal by the same angular frequency omega 0. So there is a phase shift only that is taking place. The frequency shifting property is a dual of time shifting property. The shift in one domain leads to multiplication by a complex exponentiation in the other domain. This we can confirm. Frequency differentiation property. So if instead of xt, if we take txt, if you just multiply it by time t, then what happens? The transform is just differentiated. So if you take d omega of x of j omega and multiply it by j, you will revert you revert the time domain signal as t into xt. So physical significance is if we take differentiation of the Fourier transform of the signal and take its inverse Fourier transform, then it will result in a signal which is multiplied by minus t, the time value of the signal. Convolution property. If x1t transforms to x1 j omega and x2t transforms to x2 j omega, then x1t convolved with x2t transforms to x1 j omega, x2 j omega. So means convolution in time domain is equivalent to multiplication in the transform domain and vice versa. So physical significance of convolution. We know that computation is easy to multiplication is easy to compute, but convolution is a costly affair. So if you want to do convolution in time domain, what you can do is you can take the Fourier transforms, multiply it in the Fourier domain, and then take inverse Fourier transform. Another important use of Fourier transform is to find response of the system for a given input. So suppose we consider, say, uh, example of the speech signal. There is excitation at the larynx and it gets convolved with the impulse response of the vocal tract and it generates the signal, speech signal, which is a convolutory signal. And if we want to separate out where is the excitation, or if you want to extract the impulse response of the vocal tract, then you will need to do the deconvolution. So that deconvolution becomes easy in the transform domain. Modulation property. Now in this case, we are multiplying in time domain, and in the transform domain you uh, get the convolution. So multiplication in time domain gives you the convolution in the transform domain. So multiplication in time domain, this reminds me of the fact that when there is a modulated signal, no, so cos of omega ct will be multiplied by cos of omega mt. So you get that multiplied term, and then you can take the Fourier transform, which is the convolution, and then you can plot it properly. This is what it, that is why it is actually called as modulation property, because this is made use of in the modulation. Physical significance of modulation: when the carrier signal multiplies with the message signal, uh, we can say we get the double sideband suppressed carrier modulated signal. This property says that the property of Fourier transform of the multiplied signal, which is the modulated signal, that is why, as I have pointed out, that is why it is called as the modulation property. Then the Fourier transform of the modulated signal is the convolution of the Fourier transforms of the component signal. Duality property examples. So a rectangular pulse in time or frequency domain results in a sinc function in frequency or time domain. So if I have a pulse in the time domain, I get a sinc function in the frequency domain. If I have a sinc function in time domain, I get a rectangular pulse in the frequency domain. An impulse in time or frequency domain corresponds to a constant in the frequency or time domain. So if it is the impulse that is just a straight line, in time domain you get a completely spread out spectrum in frequency domain, and vice versa. Convolution in time and frequency domain corresponds to multiplication in the frequency slash time domain. So this is what we call it as the duality property, in the sense it is same for if we change from time to frequency, or if we change from frequency to time, still the property holds good. So Fourier transform duality property: if this is x of t and this is x of omega, then if you have x of t like this, then you get the Fourier transform same as the time domain signal, with the inverse of course in frequency domain. Time bandwidth product. Bandwidth product of any signal is lower bounded. There is a lower bound, that is half, and we say Td into Bw is greater than or equal to half. That is what we say resolution in time domain multiplied by resolution in the transform domain remains constant. The maximum limit is equal to half, greater than or equal to half. It has to be, it will have lower bound, not maximum, lower bound. This lower bound indicates that the signal duration and the bandwidth cannot be simultaneously decreased. This is the significance. So if I go on reducing the time resolution, and if I go on reducing the frequency resolution also simultaneously, it's not possible. The signal satisfying the equation is with equality is the Gaussian pulse. So in case of Gaussian pulse, we have limited time duration, and we also have limited bandwidth in the free transform domain. So this is what we call it as the uncertainty principle. Parsevals relation. If xt transforms to x of j omega for complex valued xt, what happens is integration minus infinity to infinity mod of xt square dt is 1 upon 2 pi integration minus infinity to infinity mod of x j omega mod square d omega. What it means is energy in time domain is same as energy in the transform domain. Energy can neither be created nor destroyed. That is what we already know. So physical significance of Parseval's theorem. Parseval's identity states that the energy of the signal in time domain is same as the energy of the signal in the Fourier coefficients. Mod of x sub j omega square represents the energy spectral density of the signal. Right. So all these properties will also be holding good in case of DTFT, discrete time Fourier transform. So analysis of LTI system using Fourier transform and DTFT. The impulse response of the system is known in time domain. Fourier transform of DTFT can be analyzed to find the magnitude and phase response of the system at different frequencies. So if you just take the Fourier transform, you get the frequency response. The response of any LTI system to a given input is evaluated as a convolution of the input signal with the impulse response of the LTI system in time domain. As I said, the excitation gets convolved with the impulse response of the vocal tract to generate the speech signal, which is a convolved signal. So in summary, we can say that if we have continuous time signal, we get aperiodic Fourier transform. Fourier transform is aperiodic. If the signal is discrete, then you get DTFT, and this DTFT is periodic. If the time domain signal is periodic, Fourier series representation we are getting, and it is discrete. If the signal is non-periodic, we get continuous spectrum, and that is DTFS, but it is periodic. Thank you so much.